So here we have the graph of y equals sine x over x, and the limit as x approaches 0 of sine x over x appears to be 1 based on our graph. Now we can't plug 0 in to that function because this is an indeterminate limit. Sine 0 is 0, and if I plug in 0 for x, I've got 0 in the numerator and 0 in the denominator, so that's indeterminate. We could try the sandwich rule, because we did that a lot with when we had sine as part of a function. So if we graph y equals sine x over x, it appears that the limit as x approaches 0 of sine x over x is 1. We might try to prove this using the sandwich rule as follows. So we know sine x oscillates between -1 and 1. And we could rewrite the limit as x approaches 0 of sine x over x as the limit as x approaches 0 of 1 over x times sine x. So the smallest value that sine can take is -1. And if we multiply 1 over x by -1, we get -1 over x. And if we the largest value sine x can take on is 1. And if we multiply 1 over x times 1, we get 1 over x. Now the problem is that when we've used the squeeze theorem or sandwich theorem, we've been able to plug in to the other two functions. However, the limit as x approaches 0 of -1 over x does not exist. And the limit as x approaches 0 of 1 over x does also not exist. Both of those functions are hyperbolas. They have a vertical asymptote at x equals 0, and the two sides of the function go opposite directions. So unfortunately, neither of these two limits are defined, since the left and right hand limits do not match for either of those limits. We will have to be more creative. Just see if you can follow this proof. Don't worry that you wouldn't have thought of it. So we're going to rely on the unit circle, creating some triangles, and using a formula for area of a triangle. So here we have a unit circle. And I can represent any point on the unit circle as cosine theta, sine theta. X would be cosine theta, the y coordinate would be sine theta. And just to remind you why, cosine theta is the adjacent side over the hypotenuse. But on the units, anywhere on the coordinate plane, the adjacent is x. And on the unit circle, the hypotenuse is 1, so that would just be x. So cosine theta is the x coordinate on the unit circle. Sine theta is the opposite side over the hypotenuse. Of course, the opposite side is always y. On the unit circle, the hypotenuse is 1, and so that would be y. So we could represent any y coordinate on the unit circle as y. So here we have a triangle. We can represent the x, the adjacent side of that triangle is cosine theta. We can represent the opposite side of that triangle as sine theta, and the hypotenuse is 1. That triangle, however, is not the most useful for calculating anything out because we don't know what theta is. So we're going to need a few more things to help us. Specifically, we're going to need some more triangles. Now, I could extend the adjacent side. so that it was equal to the radius of the unit circle, which is 1. So now OA here is 1. So we know one side. And this triangle is now extended so that, and I've got a line here perpendicular to the radius of the unit circle, which is 1. So one side is OA and one side is AT. And we need to represent that as something, right? So AT is one side. And 1 is the other. Well, we know that tangent theta is the opposite side over the adjacent side. Well, the opposite side, so we're just looking at the blue and red triangle, the big triangle there, triangle OAT. For triangle OAT, the opposite side is AT. The adjacent side is 1, so I could represent AT as tangent theta. So if AT is tangent theta, then this point T here is the x-coordinate is 1, right? Because from O to A is 1. And then from A to T is tangent theta, because opposite over adjacent is tangent, and AT over 1 is AT, which is tangent. So now we have a way to represent T. That point T is 1 tangent theta. So we've got 3 points here. This point here is cosine theta, sine theta. And then A is 1, 0. And T is 1 tangent theta. So we have one triangle is the, I'll just outline them. One triangle that we see here is triangle OP. We didn't give that a point. We'll call it, I don't know, call it C. I didn't use C. All right, so we have one triangle there, OPC. And we know one side is 1, but it's got 2 other variables in it. One side is cosine theta and the other side is sine theta. We have a second triangle, which is triangle OAT, and one side is 1, and then one side is tangent theta, but we don't know what OT is. And you might think, well, dude, that's just as many variables as we had in the triangle OCP. And you're right, but then you're not right. Because if I think of how I calculate out area of a triangle, I don't use the hypotenuse. So it really doesn't matter that I don't know what OT is, because I do know what OA is, it's 1. And I know what AT is, it's going to be tangent theta. And so that means right now we only have one unknown, the tangent theta. So that triangle's got one unknown. The green triangle's got 2 unknowns. That's a problem. Maybe we can draw another triangle using that green triangle that would only have 1 unknown, not 2. And we're going to do that by drawing a line between P and A. So you can forget all about C that we just drew in on the other page, because you know what? He wasn't very helpful anyway. But this new line segment, AP, I think that one is going to be much more helpful to us. All right, so let's start labeling some things here. All right, so we have now triangle AOP. All right, and some things we know about triangle AOP. Well, for instance, we know that this length here is 1. We know that. OA is 1. And we know that the height of this triangle would be sine theta. So that's something we know about this triangle. Well, actually also know something about the big triangle as well. Let me go back to the big triangle here where we just had these two triangles. The green triangle and the blue triangle are actually two similar triangles, right? They have the same angle measures, right? They both have they're both right triangles, and they both have angle theta. So if you've got two angles the same as a triangle, you've got three angles the same. And so here we have two similar triangles. The trig ratios for similar triangles are exactly identical, because trig ratios are just the ratio of the sides. They're not dependent on the size of the triangle. So sine theta in the green triangle is exactly the same as sine theta, or excuse me, tangent, well, that's the same too, but tangent theta in the green triangle, it'd be the same as tangent theta in the red and blue triangle, the larger triangle OAT. All right, anyway, now let's go back to this triangle here. So we have the yellow triangle there, triangle AOP. And that triangle is smaller than triangle OAT. I think we can all agree that yellow triangle is definitely smaller than that big triangle. We also have another measurement here, and that is the sector. Right? So we have sector AOP. Now a sector is formed by two radii and the intercepted arc. Right now it's outlined in red. It has a larger area than does triangle AOP, the yellow triangle. Well, we've got a yellow triangle with some overlapping part. But when I say the yellow triangle that's outlined in blue, because there are two yellow triangles there. So that triangle there, triangle AOP, has a smaller area than does sector AOP. And they both have a smaller area than the large triangle OAT. All right? So we've got triangle OAP, which is not outlined at all. Let's outline that one in green. All right, so there's triangle AOP. It has a smaller area than sector AOP, and that one has a smaller area than triangle OAT. So we couldn't plug in and evaluate. We're going to use geometry here to help us out with figuring out the limit for sine x over x. We're going to need one more thing to help us out, and that is something called Heron's formula. So Heron's formula is another way to calculate area. You're used to this one, area equals 1/2 base times height. We have a way to represent the base of the yellow triangle there. The base was 1. We have a way to represent the height. It's sine theta. But so actually that particular triangle we could do 1/2 base times height. We're going to get the same answer as we would get using Heron's formula. But there'll be other times when we won't be able to calculate it out. So actually, I just automatically went to Heron's formula. I didn't even bother to write down 1/2 base times height. But you do get the exact same answer, which is nice. Two ways to get the same answer. Anyhow, we can use area of a triangle in this case, one that we're used to from geometry, 1/2 base times height, because we could represent the height of this triangle as sine theta, right? Because this point here was cosine theta sine theta. We could also use Heron's formula. So Heron's formula uses the fact that if you have two sides and the two adjacent sides and the included angle of a triangle congruent to another two adjacent sides and an included angle, the two triangles are congruent, to be able to find the area. So if you have two adjacent sides and the included angle, because those will always be congruent triangles, you can also use the following formula: 1/2 times A times B times sine C. So A and B are the adjacent sides, and C is the included angle. And so over here, I have Heron's formula. So A is 1. I don't know how to point it. So by the way, so this is the original got ruined. So I am stuck with the writing, other than the new writing I'm doing. So I can point, draw things, and draw an arrow to point. So that A there is 1, and B here, so there's two blue sides now red, is also 1, right? Because those are both radii of the unit circle. And then the angle is theta, so sine theta. So notice if you use Heron's formula, you get the exact same thing as you'd get with base times height. Sometimes you can't use base times height because you don't know the height. In this case, we actually did know the height. So this would be sine theta divided by 2. And this would be sine theta divided by 2. You know, all the years I've been teaching, I never have used 1/2 base times height. Because I didn't have this recorded, I went and made a new video, and I just happened to notice, oh, you know, I could have used 1/2 base times height instead of Heron's formula. That's fine. All right, now you learn a new formula. All right, so we can find so here we have the area of triangle AOP, right? And that was sine theta divided by 2. But what about the area of the sector? Right? So if you remember from geometry, the area of a sector, and I'm just going to use this handy dandy arrow to point to things because I can't write it. Well, I could write it, but I've already got it written and I can't erase it. So the formula for area of a sector is central angle over 360, the fraction of the circle, times pi r squared, the formula for area of a circle. And this is if it's in degrees, which is fine. All right, so let's plug, and this is if it is in radians, all right? So if it's in radians, you're going to replace the 360 with 2 pi. Other than that, it doesn't change at all. We will use radians, all right? So area of a sector will be the central angle over 2 pi times pi r squared. I mean, let's face it. Would you rather use 2 pi or 360? The answer is 2 pi. It's much smaller, and oh, it's going to simplify a whole lot nicer. So we can simplify that. We can cancel out the pi's. So this says central angle. This is multiplication. It almost looks like central less than r squared, but that's not what it is. Central angle over 2 times r squared. All right, well, what's the central angle? It's theta, right? We have it listed. Look at right there. See, theta. There's the central angle for the yellow sector there. And what's the radius? It's written all over the place. It's 1. All right, so we can just replace, and I'll write it over here because it doesn't look like I wrote it anywhere. I have it kind of over there, but I'll put it over here too. So central angle is theta divided by 2 times 1 squared, which is just theta over 2, right? So whether you plug in, whether you reduce in the beginning or reduce at the end, you can cancel out those pi's. So you've just got theta over 2 times 1 squared, and that is theta divided by 2. So that's the area of the sector. And we've all agreed that the sector has a larger area than does this triangle, which is right there. And now we have the third triangle, and we all agree that the third triangle has a larger area. Right? How are we going to calculate the area? Why not just use 1/2 times base times height? I could have used that in the first one instead of Heron's formula. So the base is 1, right? I'm going to outline. Here's the base of the triangle, and that is 1. And then here's the height of the triangle. So base is 1, and height is tangent theta. So the area of triangle OAT is 1/2 times 1 times tangent theta, which is tangent theta divided by 2. So now we've got the makings here of a sandwich theorem, because we've got 3 functions: sine theta divided by 2, theta divided by 2, and tangent theta divided by 2, wherein that middle one, theta divided by 2, is greater than or equal to the smaller one, sine theta divided by 2, and less than or equal to the larger function, tan theta divided by 2. And you might still be thinking, oops, I'm just trying to move the recording box, see how long this is, 22 minutes. And you might still be thinking, how does this answer our first question? Let's continue. All right, so now that recording box that I moved over to see how much time I had is smack dab in my way. All right, so we had the three functions: sine theta divided by 2, theta divided by 2, tangent theta divided by 2. Don't look much like our original question. What if we get rid of the divided by 2? Everything's divided by 2. Why don't we just multiply everything by 2 and get rid of it? All right, so if all those things divided by 2 work, so do those things multiplied by 2. So that statement is equivalent to sine theta is less than or equal to theta, which is less than or equal to tangent theta. All right, so now we're still working on figuring out how we can get back to our original limit here. Well, first of all, I'd like to replace the tangent theta and get rid of tangent theta. And let me get an arrow so I can point out what we're doing. Maybe I shouldn't use blue, but I already did. All right, so I could replace tangent theta with sine theta over cosine theta. All right. And we don't really want exactly what we've got here. So what if let's divide everybody by sine theta. What would happen if we divided everybody by sine theta? All right, so that means that this one gets divided by sine theta, and this one gets divided by sine theta. And well, dividing by sine theta is the same as multiplying by 1 over sine theta. Sine theta over sine theta becomes 1. Now down here. And then we've got is less than or equal to theta over sine theta, which is less than or equal to 1 over cosine theta. And look at this. This is so close to what we're looking for. We're looking for this. So close, but not quite. But there's this handy dandy thing. with inequalities only that you can, if you have an inequality, you can make everything the reciprocal, and it still holds, it just reverses the inequalities. It reverses the sign. So I can flip everybody. If I flip 1 over 1, surprise, surprise, oops, I just wanted to move the 1. It looks like a T. You're going to be like, what's 1T? If I divide, there we go, close enough. If I flip 1 over 1, right, I still have 1. If I flip theta over sine theta, now it's sine theta over theta. Yay, that's what we wanted. And if we flip 1 over cosine theta, we have cosine theta. You're allowed to do that. However, you have to flip the sign, right? So now the signs are the opposite. So now we've got that sine theta over theta sandwiched between 1 and cosine theta. Now it looks weird to have it be greater than and then moving the, it just looks icky, right? So let's just switch the order. So switch the ends so that looks what we're used to. So cosine theta is less than or equal to sine theta over theta, which is less than or equal to 1. Now we've got something we can work with. All right, so now we were looking and we've got something we can plug into. Now we can proceed with the sandwich theorem. So all that business with the triangles was to look at relationships and find another way to rewrite this, to rewrite our functions. So now instead of having 1 over theta times sine theta, we have cosine theta. Not something we could have gotten to directly. That was thanks to the triangles and the sector there on the other page. And instead of having, so cosine theta is replacing -1 over x. And 1 is replacing 1 over x. And how we were able to do that was the relationships on the unit circle with those two triangles and that sector. So that was our saving grace, because we can take the limit of all of these now. So the limit of cosine theta as theta approaches 0, I can plug into that one. That one's not undefined. Cosine 0 is 1. All right, so the limit as theta approaches 1 so we got the 1. We got the limit of cosine theta as theta approaches 0. That's 1. The limit of 1 as theta approaches 1 is 1. The limit of any constant is that constant. So now we've got two constants that match. Sine theta over theta is sandwiched between two functions that we can now take the limit of. Hooray! So we are in the closing here. So the limit as theta approaches 0 of sine theta over theta, since the limit of cosine theta as theta approaches 0 equals the limit of 1 as theta approaches 0, and cosine theta is less than or equal to sine theta over theta is less than or equal to 1, the limit as theta approaches 0 of sine theta over theta is 1 using the sandwich theorem. Hurrah! And the world rejoiced because we found out the answer. That the limit as theta approaches 0 of sine theta over theta is 1. And we proved it thanks to a very unlikely source, two triangles and a sector. Thank you, two triangles and a sector. And our very unconventional method here of proving it. So, and I don't need this page because I did it all on the other page, so I'm going to ignore this page. And there we go. That's the end of this video because nothing else I needed. I did it all over here. So this is the big idea. And if you'd like, I'll make you a copy of this. Thanks for watching and bye for now.